Thank you everybody for joining. I really appreciate everyone taking the time. I see someone here is joining at 2:30 a.m. their time. So thank you so much for joining. We really appreciate it. Without further ado, we're going to go ahead and get this webinar started. There'll be time for questions at the very end, but I just want to mention that we do have the Q&A feature as well as the chat feature open, and feel free to drop your questions in there at any time, and we'll get to them at the end. Also, before we get started, I want to remind everyone that you want to suggest future speakers in this series. We do have a suggestion form on our website, and I'll link that in the chat very quickly. But without further ado, I want to introduce today's speaker, Dr. Chris Rollins, who is joining us from GNS Science, where, since he joined in 2021, he has primarily been working on the New Zealand National Seismic Hazard Model. He is going to be giving a talk today on the 16 years since the great 1964 Alaska earthquake. We're very glad you're able to join us, and without further ado, the floor is yours.
Thanks very much, Juliet, and thank you so much for inviting me to give this webinar. And thank you so much to everyone that is here watching or might be watching this recording. I really appreciate it, especially the person that's 2:30 in the morning. That's strong. I am going to be talking about, so this March 27th of this year marked the 60th anniversary of the 1964 Alaska earthquake. And I'm by no means the expert or an expert on this earthquake, but this earthquake sparked a lot of things that, in terms of subduction zone science, it was kind of the original subduction earthquake in terms of being recognized as such at the time or shortly thereafter. And it has also sparked, there are some other elements of it that have implications for hazards, particularly where I live, which is in Wellington, New Zealand, and in other subduction environments around the world. So, yeah. So, as many of you are probably familiar or aware, the Alaska Aleutian Subduction Zone is just the Pacific Plate subducting under North America with some complications. But there's this very long volcanic arc with too many active and dormant volcanoes to remember, and probably too many earthquakes to remember. And Pacific Plate is moving northwards, subducting under Alaska, which is roughly part of North America, plus or minus, although it's moving in its own ways. And things are gummed up and complicated by the collision of the Yakutat microplate, which is it's not oceanic, it's like oceanic continental mixture somewhere in between, probably partially rifted off of Oregon about 60 million years ago, I believe. And then scooted northwards along the Pacific until it crashed into Southeast Alaska, and that screws everything up. And so there's different interpretations about maybe South Alaska is rotating counterclockwise with this Yakutat microplate indenter, or maybe the whole thing is escaping, sort of like Tibet and China, or maybe the whole thing is escaping, including stuff going up further up north into the Cordillera. And then there's models that also have southward flow and inferred from geodesy and a bearing plate. So yeah, things are more complicated than just a typical out-of-the-box subduction zone. But the subduction zone itself has been very seismically active, including in very large earthquakes. So most of the length of the subduction zone has ruptured during the instrumental era. And so there have been plenty of earthquakes above magnitude 8, including the 8.2 earthquake 2 or 3 years ago. And there was an 8.6 in 1957 and an 8.7 out here in 1965 at the Rat Islands. And today we'll be talking about the largest of them all that's at least been observed, which is a 9.2 earthquake that happened in 1964. And so this earthquake nucleated kind of at the near the squeeze point where the Yakutat block is really gumming up, and where it kind of transitions to a more clean subduction, but it's a flat slab subduction zone under Prince William Sound. And we'll get into some geometrical results of that later. But basically, this earthquake nucleated under northern Prince William Sound and propagated about 950 kilometers to the southwest, with an average, depending on how you calculate it, of about 15 meters or 50 feet of displacement along this entire pink section. And so it nucleated at the bottom of the seismic, or bottom of the rupture zone, and then went to the southwest. And this was one of the longest earthquakes known. I think it was the longest until the Sumatra earthquake. Shaking lasted close to 5 minutes in places, and this is an animation that can be reproduced by ground motion simulations and animation by Carl Tape. And there are places that felt shaking for 4 minutes and 45 seconds, I believe. And one of the big things about this earthquake, and possibly scientifically the biggest thing, was that it uplifted a huge portion of the land in what's called Prince William Sound, which is south of Anchorage, southeast of Anchorage. This is the epicenter. And this entire part of the mostly underwater, but some above water landscape got jacked up by several meters in the earthquake. And you can tell that this happened because there are islands, and George Plasker and other geologists went out and measured the uplift, and they found all sorts of raised seabed that's now above the water. There was also subsidence in Anchorage and the surrounding area, and we'll see one effect of that. But basically, the hazard that this uplift posed is, as probably all of you know, when you uplift the seafloor and move it around, you uplift the water column on top of it, and then the water propagates away in the form of a tsunami. And this was a catastrophic tsunami. Most of the deaths from this earthquake resulted from the tsunami. Proportionately, the worst hit place was a native Alaskan village called Chiniga. This is what Chiniga looked like shortly before the earthquake. This is from the Chiniga Corporation, which is a tribe-run corporation website. And this is, so you can see these houses, a lot of them are at the waterline. There's this schoolhouse up here on this hill. This is what it looked like a few days after the earthquake. Only the schoolhouse is remaining. And more than 1/3 of the population of this village died. And the entire village was soon relocated, or not soon, but thereafter relocated about 40 kilometers away. And the Chiniga village is sort of doing okay now, considering that this happened and then the Exxon Valdez disaster happened. So, but this was an unimaginable tragedy, and it's not something that villagers understandably like to talk about very much. Another place that was very hard hit by the tsunami was Valdez. There were some undersea landslides that made the tsunami worse than it would have been. And so some of the run-up heights around Valdez were, I think they've been measured at something like 67 meters in some of these sort of the hillsides around it. And Valdez got completely hit by that same tsunami. There was a ship, the SS China, that was docked at the wharf that was unloading. And it was a pretty tragic episode. It was unloading, the weekend supplies. This is still a pretty isolated town, pretty few hours from anywhere, especially in 1964. So they got a lot of their supplies from ships. The ship was offloading, fresh fruit and vegetables and other supplies for, the town. And it was a Friday afternoon, and kids liked to come down, and sometimes the sailors and the people on board the ship would give them gifts and treats and stuff like that from the ship. And the wharf, the earthquake happened while the ship was there, the SS China, and the ship got sucked down. I think most of the people on the ship died, and everybody that was there on the wharf, including a bunch of kids, died because the wharf got completely wiped out by the tsunami. I think about 30 people died in that. So, and the township of Valdez was moved from this old town site to over here afterwards. This is now an abandoned town site. There's a sign saying Old Valdez Town Site, and I think there's like an airfield there, but it's basically just abandoned. It's pretty surreal. And there was massive damage from the tsunami to other port towns, Seward and Kodiak. Seward was directly in the line of fire as far as this tsunami. Kodiak was further west, but it got hit by the end of the rupture, where there was another slip patch that was particularly potent. And so this is Seward, this is Kodiak, and these remind you of some of the images after the Tohoku earthquake in Japan, or other horrible tsunamis around the world more recently. And then there was that subsidence patch north of the uplift. And one of the villages that got hit by that was a place called, or got affected by that was a place called Portage, which is about 45 minutes southeast of Anchorage, on the state highway, one, I think. And if anybody went to the SSA meeting, I think last year in 2024, I think the field trip, well, I was on the field trip and they sort of cruised by Portage. It's a bit hard to see because basically what happened is the village was dragged down by this coseismic subsidence. It wasn't washed out by a tsunami, but the coseismic subsidence put it below the high tide level. So it just became a brackish marine environment, and it's not on land anymore, or it's not fully on land anymore. So the tide started to come in and they abandoned this place too. And this is what Portage looks like now. It's just rotting houses, and yeah, everybody got out of there. Nobody lives there anymore. And in Anchorage, which was and is the largest city in Alaska, there was a lot of damage from land subsidence. This is sort of one of the famous iconic photos showing 4th Street. This is very close to where the SSA meeting, I think it was right over there, was last year. And this subsided by a few meters. And this is an elementary school, which I think was fortunately unoccupied because it was 5:36 in the evening. But this is Government Hill, I think, elementary school, where that used to be one level and it's just completely. At the SSA meeting, when I arrived at the airport, I noticed you walk down to the rental car place and they have these aerial photos and this sort of timeline. And they have one from the 20s showing how small Anchorage was back in the day, and then they now have one from now showing that this help settled, but they have one from 1964. And you can see up here that it looks like the land has just sort of spilled its guts into the sea. And what that is the most catastrophic landsliding and land subsidence that happened. This is what it looked like on the ground. It's just, so this is a house, that's a house, that's a house, that's a house. And the subsidence downward is larger than the houses that it carried with it. This is a place called Turnagain Heights, and this neighborhood has never been, so if anybody was at the SSA meeting and went the path along the waterfront, which is a popular recreation path, the reason it's not settled is because that's where this was. And it was walloped so hard by this land subsidence that they've never put houses back there. There were 131 fatalities total, is the estimate. 9 from the earthquake, including I think 1 or 2 people that were in the control tower at Anchorage International Airport. But most of the fatalities were from the tsunami, including the dozens of people that were killed in Chiniga and Valdez, and other places. And there was about 300 million US dollars at the time, which would be 2 billion US dollars now, which is actually not as much as a lot of other more recent natural disasters. But keep in mind, Anchorage's population at the time was only 100,000 people. That's basically, and there was no other town anywhere near as big. So, I mean, this was sort of still a frontier. Alaska had just been made a state 5 years before. Yeah, there's always, amidst the tragedy and the destruction, there are always stories, inspiring stories of heroism and people that put other people first and did the right thing. And there's a really inspiring story from Anchorage from a lady, Jeannie Chance, who she was a radio broadcaster, and right after the earthquake happened, she went to the radio headquarters and got on and basically became the emergency responder, de facto emergency responder. There were others, but she was very involved. And so she, over the radio, asked people not to loot, and she helped connect people to loved ones that they had, that they were missing, that they couldn't find. She was relaying requests. This place needs water. This place needs, food. This place needs blankets. And, this is just from her Wikipedia article, but if you read the last line, later she would say that her dedication and calm demeanor was due to, in part, to her responsibility to reassure people that the world had not come to an end. Now, if you're in the middle of a 9.2 earthquake, which is the largest earthquake that anybody had ever, probably heard of, at that point, and especially if you're like a kid, you probably did feel like the world had just ended. And so the ability to know that, no, the world hasn't ended. We need to take care of ourselves, and we need to help others. And what can I do? That's just, that's as inspiring as it gets. And I'm going to guess that there wasn't a emergency response manual at this point. Now there are sort of courses in it, but I'm going to guess that Jeannie Chance basically wrote the book as she went, and she did an incredible job. And yeah, so the scientifically, amidst the tragedy, one effect of this earthquake is that it basically was a proof of concept of plate tectonics. The missing piece of plate tectonics was people had looked at magnetic lineations, and they knew that plates were spreading. That had been known for a few years at this point, but they didn't know where they went. And so they realized with this earthquake, and I think with a few others like the Chile earthquake of 1960, that those plates get subducted and go down into the Earth's mantle along these big volcanic arcs. And they get subducted in, among other things, these great earthquakes. And the thing that tipped the scientific community off to that is, ironically, the tsunami and the uplift of the land. These very same observations by George Plafker. Basically, George and other scientists identified that this is just part of the subduction cycle, and that this is what happens when an earthquake accommodates subduction. You get uplift out here, subsidence out here. And in the interseismic, it's sort of flipped around, and you get down drag, plus or minus. One of the aspects, kind of the main aspect that I want to talk about going forward, that there are a lot of things about this earthquake that sound alarm bells for other, subduction environments, in terms of all the multi-hazards, including New Zealand, where I live. But the one that I want to sort of focus on going forward is actually this inset of this Plafker et al. Figure, which is, so you can see, this is a cross section from A to A prime, I believe. And this is just a schematic. So you can see you have your subduction zone slip, and it's kicking up, but you see you have these other features in the vertical displacement profile. And what these are offsets from upper plate splay faults above the megathrust that ramp up towards the surface, and they also ruptured in this earthquake. And so this is just a zoom in. Sorry, it's a bit blurry, but you can see that this Patton Bay fault had 11 meters of total offset or something like that, which is 34 feet. I mean, that was a major contributor to the tsunami, as we'll see. And there were other splay faults that went. This is a more recent schematic put together by Peter Heusler. And so, yeah, the red is essentially the co-seismic rupture. It did not go to the trench, but all of these splay faults, not all of them, but several of them co-ruptured with the subduction zone. And this is this is how George Plafker and others figured that out, among other things. This is a splay fault rupture. This is, you can't get this by just regional uplift. This is a significant relative displacement across one of these splay faults. And I think it's in Hanning Bay, which is this one. And people have modeled this earthquake, including these splay faults. And so Elena Suleimani and Jeff Freimuller modeled this a few years ago. And so this is their slip distribution. on the subduction interface, which had a couple of zones of more than 20 meters of slip. And then this is their splay fault, and this is aerial view, but this thing ramps up to the southeast towards the surface, and it sunlights along Montague Island. And this is the land uplift from that. So this is the splay fault. This is the rest of it. And they found that the splay fault was a crucial contributor to the tsunami. You basically wouldn't have gotten a tsunami as bad if you didn't have the splay fault. Actually, so the splay fault had only been mapped on Montague Island and other islands around it because it's underwater. So at the time it was only mapped onshore. And Elena and Jeff found out that even if you account for this part of the splay fault, you get the black line, you don't match the wave heights that were observed in the tsunami at places like Seward. So the run up at Seward, the crest height was 6 to 8 meters. You only can get that by rupturing like the whole length of this splay fault. Seward's right there, so you have to have something immediately outboard of it, and you have to have this splay fault rupturing 400, 500 kilometers to the southwest. And so this is a big, and with several meters of slip. Same with, I believe this is in Kodiak, Rocky Bay, which had also a crest height and a run up that was consistent with more than just the onshore part of the splay fault going. You needed part of the offshore to go. And this was not the first time that the splay fault and the subduction zone ruptured in a single earthquake together. In South Alaska, Jessica DePaulis and Tina Dura and others have recently looked at this, and they went to a place on several locations around Prince William Sound and found lagoons that were kicked up above essentially like the sustainable level for having a lagoon there. And so they gradually drained after 1964. So it was full before, because it was, I think it's just a tidal lagoon, 1964, and then it was uplifted by a nearby splay fault, the Patton-based splay fault system. And then the water drained away because it was unsustainable at that elevation. And Jessica and Tina, made the connection that, maybe this happens before or after previous earthquakes on this system, and that might be an earthquake meter for rupture on these splay faults. And so the colored PDFs here so they did indeed find evidence of previous uplift in the sedimentary record at Hidden Lagoons at this same site. And those colored PDFs are those timings of those prehistoric uplifts across that splay fault system, which is right next door to this lagoon. And then these PDFs, these black lines, are from elsewhere. They are PDFs of the timing of subduction earthquakes in southern Alaska, bigger scale subduction megathrust earthquakes. So you can see that 1 out of every 3, and then plus 1964, they co-rupture. Sometimes they don't co-rupture, sometimes they do. So, one of the questions from this is, what does this imply for other places around the world where you get these upper plate faults above the subduction zone? So I live in New Zealand. I live in Wellington, which is right here. It's on the end of the Hikurangi-Kermadec subduction zone. This is just a map from our National Seismic Hazard Model. And the Hikurangi-Kermadec subduction zone, the Pacific plate subducts to the west under essentially the Australian plate plus a back arc at about 40 millimeters per year. And it's an oblique subduction zone, and it gradually leaves off of subduction capability and transitions into a strike slip fault, the Alpine fault. And Wellington is right on that transition zone, and it's kind of an overlap zone. It's a crossover between subduction hazards and strike slip hazards. Don't worry about this figure. This is the other subduction zone. But Wellington is threatened by basically everything associated with a subduction zone and everything associated with having an upper plate. So it's San Francisco if you add a subduction zone also. You have the Hikurangi subduction zone. This is the coupling coefficient in red, the red coloring, you can see there's a locked patch under the southern North Island. Wellington is right here on the bottom end of that locked patch. And all of these red faults are upper plate or surface sunlighting faults. One of them goes right through Wellington, and this is the downtown area of Wellington. I think it's a few hundred meters from the Wellington fault. And this is the airport. The Wellington fault is not, it's the closest one to town, but it's not unique. And we'll see another one later that ruptured very catastrophically about 150 years ago. But basically, you have the subduction zone, you have these upper plate faults, and earthquakes like 1964, make you think, well, what if they could go in the same earthquake? And that would probably be a worst case scenario, earthquake for Wellington. Because not only would you get, a subduction earthquake, which had, as we've seen from 1964, had plenty of landsliding, catastrophic tsunami. Wellington is not protected as much as Anchorage is, so it would feel the brunt of the tsunami from a subduction earthquake more. And then if you had a Wellington fault co-rupture with it, that would be an extreme ground motion, extreme offsets, pipeline and lifeline offsets, right along, like everyone is worried about, very near field fault displacement hazard. And it could be any of these, not necessarily Wellington, but that would be kind of a worst case scenario. And one of the things that makes you think about this a little bit is the active splay faults along in Prince William Sound in Alaska. They're right above one of the most locked patches geodetically and inferred from other means as well of the subduction zone. And so, I mean, that kind of makes sense because the subduction zone is so locked there that it starts to, strain starts to get distributed on anything that'll take it. So these splay faults are sort of spatially correlated with the most locked patch. And, this is the most locked patch of the Hikurangi subduction zone, the southern North Island of New Zealand. So, it just going by this comparison, this is where you might expect splay faults based on this, all else being equal. Actually, it's more complicated than that, but I won't get into that. So I would argue that if you need a worst case scenario earthquake for emergency planning in Wellington, I mean, 1964 is pretty much your earthquake. Now, there are a couple caveats, and that's going to be the focus of the rest of this talk, is trying to explore those more and get some other examples of earthquakes like this that we can use for hazard and understanding of what Wellington could face in the worst case scenario. So the first caveat that why you can't just stick 1964 like a finite fault model right under Wellington and model it exactly, other than that the faults are a little bit differently located, is that in Wellington, it's a strain partitioned environment, and the upper plate faults are strike slip, sort of a mode 3, not reverse. So in 1964, I mean, this is kind of easier to understand intuitively about why you would just get a propagating reverse fault rupture that just peels up onto these faults. In Wellington, these faults go in and out of the page, so the mechanics are different, and the mechanics of how you co-rupture are different. The other, and so you could imagine kinematically taking 1964 and just changing the splay fault slip to strike slip if you wanted, and actually maybe that would be useful anyway. But the other issue is what is the probability of an event like that happening in Wellington, a 9.2 with multiple upper plate fault ruptures at the same time. Is there any way to figure that out? So one of the ways that we started to explore this hazard and maybe these likelihoods are through earthquake simulator runs. I'll show you just a fly through of RSQ Sim, which is an earthquake simulator. And my colleagues, Andy Howell and Camilla Penny at the University of Canterbury, have set up simulations with all of the known crustal faults and the Hikurangi subduction zone interface. And they just run it for many hundreds of thousands of years. And so this is an example of a joint upper plate subduction rupture, so a co-rupture of Hikurangi and, in this case, the Wairarapa fault. And I'll just flip through a few examples of these joint ruptures. So the green are the upper plate fault faults that go, colored by their amount of slip. And the purple to red is the Hikurangi interface. And so these are not all of the earthquakes that happen. These are all of the earthquakes where you get a significantly non-zero amount of slip on both systems. So these are a bunch of screenshots that Andy sent me, selected from a much more rich diversity of earthquake behaviors. These are just all of the ones that happen to be co-ruptures. So I don't want to make it sound like this happens every earthquake, but you can see there's a variety of different, configurations. Some of them are quite sort of catastrophic, where you get multiple upper plate fault sources. Some of them are a bit simpler, like this one, where you only get one. So these things are an emergent behavior out of this model. And you can then plug these into ground motion prediction equations, or even ground motion simulations, like my colleague Duo Lee is doing with similar kind of scenarios, and figure out the hazard from them. And so we can use these. You can see the year, by the way, they're colored by the year. And so, if you think the physics of this model are a decent approximation of the real Earth, then maybe the frequency with which these come around in this model is not that far off of the frequency that you might want to expect something of this breed in the real world. And a little bit more insight into the physics of what might be driving these these joint ruptures between subduction and upper plate faults. So the RSQ sim is quasi-static. It doesn't solve the wave equation as far as I understand, but this is just some intuition about something that you might want to try and simulate from my colleague Iris van Zelst. So she did a full make the faults emerge from geodynamics and then slip them seismically with dynamic rupture modeling, and then propagate that into a tsunami model. You can do this full chain of different models and cascading. And so what Iris's model does is it makes the splay faults emerge from stress concentrations, and they emerge at the angles the angles to the subduction interface, they're 15 to 20 degrees. That's what you actually expect from Coulomb and stresses and principal stresses at this point. So you expect them to splay off pretty much like this. And then Iris simulates an earthquake dynamically using this as a loading state, as a pre-stress. And so, this is what you get if you don't have the splay faults. This is the slip distribution. It's a nice and smooth slip distribution. And this is what you get with the splay faults. So you can see the slip distribution. This is on the interface, on the subduction interface below all these. You can see it's much more patchy, and that's because it's feeding slip up onto the splay faults. And one of the things that Iris found in these simulations is these aren't just slip pulses that come up from the subduction zone and just tear up. There's actually a lot of the slip on these splay faults happens through kind of like backwash and reverberation of the accretionary prism. So the blue, sorry, I should explain this better, but the blue is slip per time. Time is going up vertically. And so if it was just one pulse going up each of these splay faults above the subduction zone, it would just be a blue line going that way. But you can see there's a lot of reverberation as waves, and that makes what waves reverberate around the accretionary prism, and that initiates more slip. And so you can kind of get secondary slip pulses, and that makes sense because it's basically dynamic self-triggering. Now, those models are very useful for hazard and what could happen and why it might happen, those simulations. We still want to look at data and compare them to the real world and try to get a sense of like, all right, how realistic is an earthquake source like this, and how often might we expect it to come around? And so what Camilla and I have been looking at are real life examples of joint ruptures, particularly mixed mode joint ruptures, but not necessarily limited. There's a couple in New Zealand. The 2016 Kaikoura earthquake, it was a 7.8 earthquake, very complicated, and then the 1855 Wairarapa fault earthquake. So probably have to go a bit fast, but the Kaikoura earthquake was a very complicated earthquake with more than 10 meters of slip on several, or more than a few meters of slip on several upper plate faults directly above the southernmost Hikurangi subduction zone. It's the magenta one here. And there was also a lot of coastal uplift, and this is one of the faults, the big ruptures in the earthquake, the Papatea fault. You can see that both sides of this fault are uplifted, and so it's sort of the reverse of that Hanning Bay splay fault case. If both sides of a fault are uplifted, something's got to be uplifting it from below. And there are also geodetic measurements that show, region-wide uplift in the Kaikoura earthquake. And so a number of modelers have fit the slip distribution in the Kaikoura earthquake from a variety of different data sets, tsunami, geodetic, seismologic. And some of these models have slip on the subduction interface that these faults root into. So on the southern Hikurangi. Now, sorry, it's a bit hard to see, but these are 4 different models, and these are the upper plate faults colored by their slip. And this is the subduction interface. It's an aerial view. You can see these models don't agree at all really about where the subduction interface slip should have happened. And so it's hard to resolve. It's kind of in the null space, but recently Matt Herman and other co-authors have looked at the aftershocks following the Kaikoura earthquake, and they found a lot of subduction aftershocks. So this thing, the subduction interface is, it's capable of seismicity, and it's kind of hard to imagine how it would have had a bunch of aftershocks while remaining completely silent in the earthquake before. So it probably had some slip, in my view. So this was probably a joint rupture, kind of a mild joint rupture, because the main action was, this 5 to 12 meters of slip on these upper plate faults. But one of the things that Matt and others connected is that maybe the slip on these upper plate faults was so extreme because they were kind of pried out. They were pried open by subduction slip beneath them, and slip here was much more just sort of normal 2 to 5 meters, and those are not above the seismogenic part of the subduction interface. And so, maybe the ones above the interface had extreme slip because of prying open by interface slip below them. And that's something that, if that's true, you would want to watch out for in any joint rupture, regardless of mixed mode or just splay faulting, anything like that. And so the other earthquake in New Zealand, that's a well-known or well-evidenced sort of joint rupture, is this Wairarapa Fault earthquake in 1855, which is the largest earthquake that's ever been inferred or observed in New Zealand. It was an 8.2 earthquake. It was mostly strike slip, but one of the reasons it was 8.2 is because it had a maximum of 19 meters of strike slip displacement. This is a world record for at least strike slip, except onshore strike slip. Now it's been broken by Wharton Basin, but it had consistently north of 10 meters, 12 meters, 13 meters of displacement along a long stretch of the Wairarapa Fault. So extreme slip. And it also uplifted the coastline and the area, the land surface around Wellington in a way that decreased to the west and is consistent with slip on some sort of underlying structure at depth. And actually this uplift, the highway that you take from Wellington to go to the Hutt Valley, which is where GNS's main office is, was uplifted in this earthquake. And it was, I think it was not very good shoreline before this earthquake, but this earthquake uplifted it by, 1 to 2 meters. And now there's a motorway there, which is maybe a bit worrying. And I always kind of hold my breath whenever I'm driving on that motorway. But yeah, so John Bevan and Des Darby modeled this a number of years ago, and they figured out that this uplift pattern does require slip on the deeper part of the Hikurangi subduction interface, as well as extreme slip on the Wairarapa faults. And that's actually this earthquake that Andy and Camilla simulated is kind of a dead ringer for the Wairarapa fault. You get high slip on the Wairarapa fault, sorry, for 1855. You get high slip on the Wairarapa fault. And then this sort of milder slip on the subduction interface, and it is only down dip basically of the fault intersection. This part you wouldn't actually have observed probably from the surface at the time. And then Rogers and Little looked into this and they started thinking, well, what if there's a connection between the fact that this was a joint rupture and the extreme slip? So basically, the slip in this is so high that it kind of is more reminiscent of like little square earthquakes, magnitude 4 and 5 and 5.5, where the slip does not saturate. It's more reminiscent of that than it is of these big earthquakes where the slip just keeps propagating for hundreds of kilometers. And so, well, what if the reason for that is because this was actually a square rupture, not a long strike slip San Andreas kind of rupture. And it would have been a square rupture if the interface has slipped along with the Aotearoa fault. And so that might explain that kind of extreme slip dimensionality. That's actually also reminiscent in a different way of Matt Herman's argument about Kaikoura. Maybe these faults were physically pried open by the interface below them, and that's why they had so much leeway to slip to 12 meters in the Kaikoura earthquake. And that is reminiscent also of something observed in 1964, which is that you had 11 meters of slip observed at the surface on the Patton Bay Fault. That is, I mean, in itself pretty extreme. And so, maybe there's a connection between action at depth and high slip on these splay faults. And that implies that, if this were to happen in Wellington, not only would you get, the Wellington fault earthquake that you would need to model would maybe need to be pretty massive in terms of the fault displacement, which makes it even worse. So we started looking elsewhere in the world because that's just sort of two earthquakes and they're both in New Zealand. There are other interesting examples of joint ruptures elsewhere. And I'm kind of running out of time, but Maule, Chile, 2010, had probably co-seismic slip on a back thrust fault system called the Santa Maria fault system. It was observed 2.5 hours after the main shock. So if you were to model it, for most hazard purposes, that's co-rupture. And so there was an interesting smaller earthquake in Chile in 2011 where Steve Hicks and Andreas Rietbrock recognized that there was a normal faulting component that went about 12 seconds after the main subduction thrust rupture. After Tohoku, and this was another one of the motivators, there was a lot of upper plate earthquakes. You can see these focal mechanisms here, and some of these were quite large, magnitude 6 and above, and they caused, I think, damage and displacement in their own right. Joan Gomberg and Brian Sherrod actually did a pretty systematic study of this in 2014, and they looked at great subduction earthquakes and then upper plate earthquakes that followed them in the surrounding regions. And basically the takeaway from their study is the 9s and the 8.8s and the 8.6s pretty reliably trigger upper plate aftershocks like these. When you get below an 8.6, it's kind of a mixed bag. Some of them trigger upper plate aftershocks in the surrounding areas. Some of them don't at all. You can see Tokachi earthquake in Japan in 2003. That was just silence in the upper plate afterwards. No aftershocks observed. And that's Japan in 2003. I mean, it's very well instrumented, presumably. And in the companion study, Brian and Joan looked at whether Puget Sound faults might have gone with the Cascadia subduction zone. There was a big cluster of earthquakes on the Seattle fault and other Puget Sound region faults around 900 AD or 900 CE. They found it probably was not correlated with Cascadia megathrust ruptures. Those are in red and in blue. And these you can see these come in a gap between. So there's probably not a correlation, but there is a slight correlation in general. And maybe the most interesting case, one that I actually just discovered, is Iquique in Chile in 2014, where it was actually an upper plate earthquake that kicked off the entire sequence. And this was a this earthquake, this is the focal mechanism. This is the focal mechanism of the eventual 8.1 that caused the tsunami and was the main earthquake in the sequence. But this 6.7, you can see it's at a high angle to the subduction zone. And so, I mean, this is sort of a mixed mode joint rupture. I mean, there's a lot of different things going on here mechanically, and maybe there's stuff we can learn from this that we might not learn from more kind of just straight up thrust and normal, ones that you can recreate in 2D. This is a fully 3D mechanical situation. And so that maybe has a lot to teach us. So just going forward, Camille and I are going to be looking for more global examples of mixed mode joint ruptures in strain partition environments. And how often those happen with respect to other earthquakes and that aren't joint ruptures in those regions and around the world. And by the way, if anybody watching this knows of a mixed mode joint rupture that I haven't included here, please holler, because we're trying to scrape the literature for all of these. And so there's a lot of questions going forward. Are mixed mode joint ruptures, do they happen the same way as single mode joint ruptures? Is it a rupture tip propagating? Or is it more of Iris's findings about trapped waves in the accretionary prism and static stress transfer and dynamic stress transfer? Does that still work if it's a mixed mode rupture where it's coming out of the page instead of a all mode 2? And can you simulate mixed mode joint ruptures in sort of pseudo 2D where it's only the slip and the D sub C and the slip distance that you have? Maybe you can do it where you only have, those are the only things you have to model in and out of the page, rather than having to model the entire 3D fault. I don't know if that's possible. So yeah, those are things that we want to look at going forward. And one other lesson that I just want to point out of the 1964 earthquake is that the worst impacts of earthquakes often happen off of camera and off of what Hollywood would maybe make a movie about. They often happen to marginalized communities. Chiniga, they didn't even know that it had been hit by the tsunami for a couple of days after 1964. Sorry, they being the news corporations and people in Anchorage, because it was a Native Alaskan community that was, a fishing based, and it didn't have road access to anywhere. And a third of the population, or more than that, died in this earthquake. This was a horrible tragedy for this village. And that's just a takeaway of this and other earthquakes, is that sometimes you have to kind of, it's not always the first headlines that are the most tragic and gripping, and maybe the most have the heaviest implications for future earthquakes. Often it's marginalized communities that are kind of on the periphery. So I'll stop there. Thank you very much for watching, everyone, and I'm happy to take any questions. And sorry for saying one long sentence for 50 minutes, but yeah.
Thank you so much, Chris. The floor is now open for questions. We already have a few that are coming in. It looks like our first is from Rob Witter, who says, I'm fascinated by splay faults. Thank you for such an interesting review. First, how do you define a splay fault? Second, can splay faults rupture independently without slip on a megathrust? Other possible mixed mode rupture 1899 Yakutat earthquake sequence.
Thank you, Rob. I was thinking about that. 1899. And I think, it's sort of, it seems like the earthquake was too big to possibly have just been on just upper plate faults. So that's interesting one. And that's a strain partition environment where crazy stuff is going on, like New Zealand. So that's probably one to include. So let's see. Let me see if I can find this slide that I was going to show. This is a slide by Peter Heusler from his 2015 paper. Hopefully, can you guys all see that? And so Peter did a compilation of splay fault ruptures. Sorry, I'm having trouble minimizing the chat. or the Q&A. There you go. So yeah, these are splay fault ruptures, some of the best examples from around the world that Peter compiled. So these are all splay fault ruptures. I don't know if I would call all of these joint ruptures. I mean, in the way that Wellington should be worried about. So what Wellington has to really worry about is a fault in the back door, in the backyard, coming up to the surface, rupturing at the same time as the subduction zone. So I would say Maule and 1964 have that. Ecuador and Tonankai are a little bit more kind of a measured transition into a splay fault where, the tsunami would be worse from this splay fault than just from straight up subduction interface. But you wouldn't have to probably worry about fault displacement hazards because this is probably still offshore. But this is still important to know because all of these are kind of on a gradient of, of what can happen. And actually, yeah, Peter might be the best person to talk about to ask about how you define a splay fault rupture. Camille and I went kind of down the rabbit hole of, and we're still going to do this, of like what constitutes a different enough earthquake to constitute like a joint rupture. Like, does this have to be does the upper plate fault have to be magnitude 6.5 and above, or does it have to represent a hazard on its own if you modeled it? As far as, so for your question about, are there earthquakes that splay fault ruptures without the subduction? So one of those in New Zealand was the 1931 Napier earthquake that ruptured a bunch of splay faults up near here. It's actually New Zealand's deadliest historical earthquake. And I think it's pretty, well, the subduction interface is deeper there, but I think it's pretty well evidence that it didn't rupture in 1931, that it was just splay faults above the interface. And so, yeah, sorry for the faffing around trying to get that slide up. Yeah, thank you, Rob, for your question. Great question.
Thank you. We still have time for about one more question if anyone wants to put one in the chat or use the Q&A feature. While we're waiting for people to potentially be typing, I do want to go ahead and thank everyone for joining, and thank you, Chris, for that fantastic talk. It will be up on the SZ4D YouTube channel if any of you want to watch it again or send it to your colleagues and friends. Speaking of, we do have a last question from Jay Patton. So the Napier fault souls into the megathrust?
That's a good question. I actually need to remind myself. The fault is called the Pukawa fault, Poukawa. I actually have not done enough reading on it, so I'll race you to find a paper about whether it souls into the megathrust or not. Good question. Thanks, Jay.
Thank you. And yes, as Anais just put in the chat, on Monday, there's the public forum focusing on SZ4D activities. The link is in the chat, and please join us if you would like.
We'll be talking about many ways for you, the community, to engage, and we'll be providing updates on our funded proposals and those who are pending, and more upcoming activities. So please join us on Monday. And thank you all for joining.
Yeah, thank you very much, everyone.
Thank you, Chris.
Thanks.
Thank you, Chris. If anyone has any last minute questions or questions that you didn't have a chance to ask today, please feel free to send us an email and we'll make sure that it gets to the right person. And so without further ado, thank you so much. And I hope you all have a fantastic rest of your day. And for those of you joining us midnight, fantastic rest of your night. Thanks.
Bye, everyone. Thank you.
Thanks.